Good afternoon. I'm Min Seok-jeong from Korea University. I'm glad to present our paper, Precise and Scalable Point Analysis via Data-Driven Context Learning. This is a joint work with Seun Jung and Hak-Ju Oh. In this presentation, I will explain our approach with call size sensitivity, but it can be generalized to other kinds of context. Not only point-to analysis, although static analysis needs context abstraction, because it is impractical to consider all the method calls separately. Without context abstraction, we should consider all the exponential cases of method calls. And the widely chosen way is most recent k context abstraction. It keeps only the most recent k context elements. For example, method M2 here with context 2 means method M2 with context 0, 2, and 1, 2. Method M3 with context 4 means method M3 with context 0, 2, 4, 0, 3, 4, 1, 2, 4, and 1, 3, 4. However, most recent k context abstraction has a serious problem that it often abandons important context elements. Let's assume blue ones are important and gray ones are useless context elements, and k is 3. In this example, most recent k context abstraction abandons all the important context elements because they are not in recent k. Let's see the problem with an example. This program has recursively defined the identity function ID, which calls itself I times and returns first parameter v. Main method gets I from user and calls the ID method with new a and I at invocation 8 and new p and I at invocation 9. There are two queries asked if downcastings at line 8 and 9 are safe. And they are obviously safe because ID is an identity function. To analyze this program, we need context abstraction because we cannot determine the value of I statically. Without context abstraction, ID method will recursively call itself at invocation 3, and it will keep updating context on and on. And to prove the queries, all the ID methods should keep important context elements 8 or 9 to distinguish ID methods called from 8 and ID methods called from 9. However, most recent k context abstraction cannot prove the queries whatever k is because it eventually abandons all the important context elements. As a result, ID method with context all 3 will return both new A, and new B to invocation 8 and 9. Thus, analyzer cannot prove the queries. What I want to say in this talk is that we should abstract the context with not most recent k, but most important k. In this paper, we propose context tunneling, a new way to achieve most important k context abstraction. With context tunneling, one CFA can prove the queries. I will explain it. This relation means main method calls ID method. When main method calls ID method, it generates important context elements. In that case, calling method updates context as usual. And then ID method calls ID method. When ID method calls ID method, it generates useless context elements. In this case, calling method does not update context, but does inherit context from caller method. We call it we applied context tunneling. Then analysis reaches a fixed point. Now we have a very good context abstraction. In this context abstraction, ID method with context 8 means ID method with context 8, 8.3, 8.3.3, and so on. ID method with context 9 means ID method with context 9, 9.3, 9.3.3, and so on. Now we can prove the queries. First parameter of ID with context 8 is new A, and it will be returned to invocation 8. First parameter of ID with context 9 is new P, and it will be returned to invocation 9. With context tunneling, one CFA becomes as precise as infinite CFA in this example. Although context tunneling can give a desirable context abstraction, it is very difficult to apply context tunneling properly in practice. If you apply context tunneling incorrectly, key context elements will not be generated. For example, if you apply context tunneling when main method calls id method, key context elements 8 and 9 will not be generated. Missing tunneling opportunity also makes it imprecise. If you do not apply context tunneling when id method calls id method, key context elements will be erased because of unused context elements. As you saw, context tunneling abstraction is a set of relations between methods which determines when to apply context tunneling. And manually finding tunneling abstraction is difficult because there are too many cases to consider, but only a few tunneling abstractions actually work. In our example, this is the only tunneling abstraction works. So, our solution is data-driven approach. With parametric static analyzer and training programs and atomic features, our data-driven framework automatically generates tunneling heuristic. Tunneling heuristic consists of two Boolean formulas, fcolor and fcolly. They express high-level properties of methods where context tunneling should be applied. For example, if a calling method has feature like fcolly, analyzer applies context tunneling. This slide shows performance highlight. We applied our tunneling heuristic to hybrid one object sensitive analysis. In these graphs, x-axis denotes number of alarms, and y-axis denotes time elapsed. For both axes, the lower is the better. With our tunneling heuristic, hybrid one object sensitive analysis becomes faster than original and becomes more precise than two hybrid object sensitive analysis, which is very expensive. Now I will talk about details. I will define static analysis with context tunneling and explain how to learn tunneling heuristics. We assume static analyzer F takes tunneling abstraction and returns proven queries and time elapsed. Tunneling abstraction here is a set of relations between methods which determines when to apply context tunneling. If tunneling abstraction is an empty set, it is the same with most recent case context-sensitive analysis. If you apply context tunneling to all method calls, it equals to context-insensitive analysis because all the methods will have the same context. From now, I will use H to denote our parametric tunneling heuristic. Our parametric tunneling heuristic takes two steps. First, it represents methods as feature set, and then it generates a tunneling abstraction. Features are predicates over method. AI here is the function from method to a Boolean value. We used 23 syntactic features in this work. For example, is innerclasses method, has store instruction, takes void input, and so on. Now I will explain how our heuristic works. Let's assume a program has four methods, M1, M2, M3, and M4. And we have two atomic features, A1 and A2. And parameter pi has two Boolean formulas, F1 with A1 and A2, F2 with not A1 and not A2. First, methods are represented as feature set like this. In this example, F1 means singleton set M1, and F2 means singleton set M4. And then heuristic generates method relations that are color method in F1 or calling method in F2. In this example, tunneling heuristic generates method relations that color method is M1 or calling method is M4. With tunneling abstraction, analyzer selectively updates context. If method MA calls method MB, analyzer checks if method relation MA and B is in tunneling abstraction. If it is, calling method inherits context from caller method. If not, it updates context. Now I will explain how to learn tunneling heuristics from codebase. We obtain tunneling heuristics by solving optimization problem. The goal of optimization is to find F1, F2, which maximizes precision while scalable than analysis without context tunneling over codebase. The main difference of context tunneling is non-monotonicity. Many learning algorithms assume monotonic relation between precision and abstraction in parametric static analysis. For example, applying flow sensitivity to more variables implies better precision. However, algorithms assuming monotonicity do not work in context tunneling because applying context tunneling to more method calls does not imply increase or decrease of precision. This graph shows how precision changes over parameters. X-axis denotes parameters, and y-axis denotes alarms. And as you can see, greedy algorithms do not work in this space because they will end up with a suboptimal result. To handle this non-monotonicity, we made a specialized learning algorithm for context tunneling. This graph shows how precision of Lundy heuristic changes over training progress. And instead of greedy search, our learning algorithm repeats exploration and exploitation to avoid local minimas. In this graph, red line expresses greedy strategy, and as you can see, its precision only increases over training progress, but its end result is suboptimal. However, our non-greedy strategy eventually find a far better parameter after learning. So far is our learning algorithm's intuition. For more details, please consult with our paper. Now let me show you the evaluation. We implement context tunneling on the Duke Java point analysis framework. We used 4 flavors of context sensitivity: selective hybrid object sensitivity, call size sensitivity, and type sensitivity. We used the Dakapo benchmark suite for training and testing. We used 4 small programs for training and tested the Lundy heuristic against other programs. And we learned and applied tunnel heuristic for context depth 1. This slide shows the effectiveness of our Lundy heuristic against testing programs. In this slide, we used selective object sensitivity, but we achieved similar results for other kinds of context. In these graphs, black dots mean selective 1 object sensitivity, blue dots mean selective 2 object sensitivity, and red dots mean hours. In this graph, x-axis denotes number of alarms, and y-axis denotes time elapsed. And as you can see, hours are the most precise and the most scalable. Unexpectedly, our learning algorithm reproduces heuristic of prior research. Milanova et al. Said that deeper object sensitivity may be useful for methods that belong to sub-object. In our case, the heuristic corresponds to context tunneling may be useful for methods that belong to sub-object. In object sensitivity, context tunneling is applied if base object of calling method is allocated in F1. And a clause of F1 said that if constructor method allocates sub-object and store it to each field, methods belong to the sub-object needs context tunneling. Now I'd like to summarize this talk. Do not keep most recent K. Instead, keep most important K. Thank you.
Can you say more about what were the 23 features you used and which are the important ones?
Okay. These are 20 features that I used. These 10 features are signature feature that method has this string or not. These are top frequent word that a signature string has. And these are features that I made. For example, if method is analysis method or method taking multiple arguments, and in object sensitivity, analysis method is a very good feature for tunneling. For example, if calling method is analysis method, context tunneling is good. Yeah, calling works well.
So which ones are the important ones?
Method contained in inner class.
Actually, I have one question.
Okay.
Have you tried using the output of your complex tunneling analysis into a client analysis like paint analysis or something and see what kind of difference it can make in
I
precision?
did only point analysis.